Hello everybody, welcome back. This is video lecture 22.1, our first video lecture for chapter 22, which is entitled Electrostatic Fields. So we're starting to get into some pretty interesting and abstract concepts. So we're going to be focusing on the first two sections of chapter 22 in this lecture, where we introduce the definition of the electrostatic field, often just called electric field for short, although technically electrostatic field is better. And then section 2, the electric field due to a charged particle. But first, before I go into all this content in my slides, let me try to motivate the concept of an electrostatic field by going back to something we talked about in chapter 21, in fact, the heart of chapter 21, and that is that if I take 2-point particles that each have some amount of electric charge, particle 1 with electric charge Q1, particle 2 with electric charge Q2, and they're physically separated from each other by some distance r. They are not in contact. Yet we talked about, with Coulomb's law in chapter 21, how either particle exerts an electrostatic force on the other. Let's just say, for the sake of argument, that both particles have positive charge. And I could ask you then to sketch the arrow representing the electrostatic force on 1 due to 2. Which way would you draw that arrow, and where would you put it? That's what we need to know from chapter 21. Well, if I want the electrostatic force on 1 due to 2, I anchor the arrow on 1, and if I've assumed both particles are positively charged, then the force is repulsive. So the force on 1 due to 2 is directly away from 2, and I was labeling that F12. Okay, and we learned with Coulomb's law the mathematical procedure for calculating that force. You need to tell me what Q1 and Q2 are and the distance r. But now here comes a deeper question that maybe was bothering you. How is it that particle 2 exerts a force on particle 1 without them being in contact with each other? There's empty space between them. They're not touching. There's a distance r between them. How can particle 2 exert a force on particle 1 without even being in contact? Seems like magic, doesn't it? Newton grappled with the same question in the gravitational case. If I have two particles with masses, m1 and m2, then each exerts a gravitational force on the other, even if they're not touching. Or the sun exerts a gravitational force on the earth, and they're not touching. Newton really grappled with how that could be. How could one object exert a force on the other without them being in contact? He did not like that at all. He thought it seemed like magic, mysticism, which the scientific part of him didn't like. So, we're faced with a conundrum. What is the physical mechanism by which, let's go back to the charge case, charge 2 exerts a force on charge 1 without them being in contact? And this concept of an electrostatic field was really came in its own in the 1800s. And the logic goes like this. Each of these particles, let's start with particle 2. Just because of the fact that it has charge and is sitting at a certain location in space, creates in all of space around it, all of space, what's called an electrostatic field. The electrostatic field is created by charge 2, merely because particle 2 has charge. That's all that has to be. It has to have some amount of charge. Then it creates what's called an electrostatic field in all of space around it, including at the location where particle 1 happens to be sitting. In other words, particle 1 is kind of immersed in the electrostatic field created by particle 2. And it is this electrostatic field created by particle 2 that ends up exerting the electrostatic force on particle 1. And of course, it goes the other way too. Particle 1, by virtue of it having charge, creates an electrostatic field in all of space around it, including at the location where particle 2 happens to be. And particle 2, therefore, is immersed in the electrostatic field of particle 1, and it's that electrostatic field of particle 1 that would exert an electrostatic force on particle 2, which would be that way, and which we would label F21. Okay, so it's this quantity called electrostatic field that a charge creates, and it's a property of space then, created by the charge, that any other charged particle can be immersed in. So the whole purpose of this chapter is practice with calculating this electrostatic field created by a charged particle. And it's got a different value at different locations. So we got to be able to calculate that electrostatic field created by a charged particle wherever we're told to calculate it. Now, before we jump right in to calculating electrostatic fields, let's warm up just a little bit with the concept of field more generally. A field in physics and mathematics, it's not the agrarian meaning of the term or the agricultural meaning of the term. It's a meaning of the term in physics and mathematics. A field is any quantity with a well-defined value, that means it could be measured with the appropriate instrument, at every point in a region of space at a given instant. So we're talking about a whole region of space, not just one point, but a whole region. And there's a well-defined value for some quantity at every point in that region. And that whole set of those values at all those different points together is called a field. Now for us, fields come in two varieties: scalar fields and vector fields. Let's give an example of a scalar field first. Scalars are easier to deal with than vectors, as we know. Well, an example of a scalar field is any region of space where at every point in that region, you're measuring a scalar quantity. An example would be the temperature of a fluid in a certain region. Remember capital T? So what I've drawn here is a side view, a little drawing, a schematic, of a side view of a big pot of water. That's what the blue is. That is sitting on a heating element right down there at the bottom. That is heating the water. Because the heating element's somewhat small, though, the temperature of the water is not the same at any given instant throughout the whole body of water. And so we could, with a small enough temperature probe, go from point to point inside the water, like there, and 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 go on and on and on, and measure the temperature at each location, and make a big table, if you like, where you give me, I put the location, and then the measured temperature, say in Kelvin, at that location. Now, to tell you the location, I've got to tell you the coordinates. So I need a set of axes. So the way I set this up was the origin was at the heating element. There was an x-axis going to the right. Okay, a y-axis going into the screen, so you can't see it in this side view, and a z-axis going vertically up. And so any given point, like right there, has some set of coordinates, x, y, and z, to tell you where the point is. And then you can put your temperature probe there and measure the temperature, and then you will have the temperature at that location, at that set of x, y, z. And you got to measure that temperature at all the points where the water is, which is a lot of points. And that whole set of all those temperature values, one value for each location in the water, is called a temperature field. Okay? All right, now let me give you an example of a vector field that is still a little bit easier to visualize not quite so abstract as the electrostatic field. So here comes an example of a vector field. Of course, what that means is, throughout a region of space, at any given point, you're measuring some vector quantity with, as we know, a magnitude and a direction. So a kind of mundane example that's easy to visualize of a vector field is the velocity of a fluid in a region, v arrow, as a function of x, y, and z. So imagine in this picture that you're looking down from above on a stream of water, where the water is flowing from our left to our right. And it's a smooth flowing stream. And we could go at any given location in the water, like there, or there, or there, or there, or there, and ask and measure what's the velocity of the water, v arrow, with a magnitude and a direction. And this picture is showing a bunch of those arrows to represent the velocities at the points where the tails of the arrows are, like there, and there, and there. And the arrow has a length, actually even a size to represent its magnitude. The bigger the arrow, the bigger the magnitude. And it has a direction to show the direction of the velocity. And at every point in the region where the water is, you've got a vector quantity, a velocity, with a magnitude and a direction. Okay? And now again, in order to give you location, you need a set of axes. So here again, I just rather arbitrarily pick the origin to be in the center of the stream, with the plus x axis going to the right, the plus y axis going upward in the plane of the screen. Then the z-axis will be coming out of the screen towards us. And my arrows represent the sample of the velocity vectors in the z equals 0 plane, the xy plane. But you could go down below the surface, beneath, and then you'd be at negative z values. You could still ask, what's the velocity of the water at the points below the surface? Okay, but that's an example of a vector field. A little bit harder to deal with than a scalar field, because at every point in the region, you've got a vector quantity with a magnitude and a direction. And you've got a huge number of points. So you've got a huge number of vectors to have to deal with, which can be a little bit daunting. It's one of the reasons why we draw pictures like this, just to help us visualize what some of the velocity vectors look like. This picture tells us that the velocity is faster, all the velocity vectors are to the right, and the velocity is faster in the middle of the stream and gets less as we go towards the banks on either side. By the way, in the previous drawing, you might have wondered what those curved lines were. Those are isotherms. Those are lines along which, in the water, the temperature has the same value. Just to help you kind of visualize the temperature distribution. Because with fields, we need a way to visualize the values, because there are just so many of them. All right, now I want to talk about another vector field. I'm getting closer to the electrostatic field, but I want to introduce something that we could have introduced last semester, but we just really didn't need it at the time. Now it's going to be helpful to talk about. And it's the concept of the gravitational field. I mentioned how Newton was concerned about how two masses could exert gravitational forces on each other without being in contact. Think of the sun and the earth. As I said, the sun exerts a gravitational force on the earth. How does it do that without actually touching the earth, which of course would be catastrophic for all of us? There was no answer to that in Newton's time. But now we know how to think about it. The sun, just because it has mass, creates what's called a gravitational field in all of space around it. And Earth is immersed in that gravitational field of the sun. And it's that gravitational field of the sun that exerts a gravitational force on Earth. Let's apply that same thinking to Earth itself, because Earth is a body with mass. How does Earth keep Moon in orbit? By a gravitational force. How does it do it? The Earth, by virtue of its mass, creates, throughout all of space around it, a gravitational field, The moon is immersed in Earth's gravitational field. And it's Earth's gravitational field that exerts the gravitational force on the moon. Okay? So I want to talk a little bit about Earth's gravitational field. So I've got a snapshot of Earth. I've got a coordinate system that's going to be very important when we work with fields. The origin is at Earth's center. And how you pick the coordinate system, by the way, is pretty much arbitrary, but you got to pick one and then pick a coordinate system and then be consistent. So I chose the plus x direction going to the right in this picture, the plus y direction going vertically up, if you like, through the North Pole, and then the plus z direction will be coming straight out towards us. All right, now simply because Earth has mass, it creates a gravitational field in all of surrounding space. And I've taken a point that I've marked, I'll draw it here so it's bigger, with an X up above Earth's surface. And that point, first I have to tell you its location. I got to tell you its coordinates, X, Y, and Z. Alternatively, I could tell you its position vector, R arrow, which points from the origin out to that location. Now that point with the red X is just a point in space. There doesn't have to be any actual thing there yet. And at that point in space, there is a gravitational field, which is a vector field with a magnitude and a direction, due to Earth. All right, here comes its definition. The gravitational field, at that point I've marked with the red X, first of all, it's a vector field, and it's going to be represented by the symbol G arrow of R arrow. We've got to get used to that notation. G arrow, you're used to seeing that before, right? If you have a really good memory from last semester, you know that we call little g either the acceleration due to gravity or, later on, the gravitational field strength. Now we're making that little g into a full-blown vector. See the arrow on top? And then when you write this, the R arrow in parentheses, you're saying that the gravitational field vector is a function of position. Where is the point X located? Okay? All right, so the gravitational field is a vector field represented by the symbol G arrow of R arrow, and its physical interpretation is, okay, gravitational force per unit mass. Per means divide, right? At the location where the X is. Gravitational force per unit mass there. Note then the SI unit of gravitational field would be the unit of force divided by the unit of mass, Newton per kilogram, which is equivalent to a meter per second squared. But it's more telling to say Newton per kilogram because gravitational field is, in essence, by definition, gravitational force per unit mass, Newton per kilogram. Okay, now that gravitational field vector, I'm now going to draw it. I'm going to erase the R arrow because there's too much going on there. The gravitational field vector at the point marked with an X is a vector quantity that points directly towards Earth's center. Gravitational fields for spherical objects like Earth always pull directly towards the center, always point directly towards the center. That's the gravitational field, G arrow of R arrow at the point where the X is. All right. Let's say I've told you the magnitude and the direction of that gravitational field at the point X. We know the direction. It's towards the center, towards the origin. Here's where the next big step is. Suppose somebody comes along with their favorite pet particle that has some mass m, and they place it at the point where I had the red X. Okay? Place a particle of mass m at the marked location in Earth's gravitational field. So now there is an actual particle put there. It's got some mass m. If I know the gravitational field, G arrow, at that point, and I do from the previous step, then it's easy to get the gravitational force on that pet particle due to the gravitational field. F grav, as we would have called it last semester. Arrow. Remember little g, arrow, gravitational field, is gravitational force per unit mass at a given location. So to get the gravitational force on your pet particle at that point, multiply g by the mass of your particle. If g is in Newton per kilogram, multiply by something with units of kilograms, and you've got a force. So if you know the gravitational field g arrow at any point, and then somebody comes along with their favorite pet particle and puts it there and tells you the mass of their pet particle, m, then m times g is the gravitational force that that pet particle will experience. And note, since m, of course, is a scalar, mass is a scalar, and it's positive, the force vector, F grav, is in the same direction as the gravitational field vector, g. Okay, so with knowledge of gravitational field at a given point, then you can calculate the gravitational force on any particle that's put at that point. Now we're going to do the exact same thing, except the property that we're going to be studying to make the field is not mass. Mass creates gravitational field. The property we're now going to be studying is charge. Charge creates electrostatic field. So here we go. Now we're ready to define electrostatic field. First, let me tell you in words its definition, and let's get you used to its notation. It's a vector field, and it's denoted E arrow of R arrow. Right there, I'll write it up here. Capital E arrow for electric field, and when you write with the R in parentheses, which sometimes we write and sometimes we don't, it's just a way to convey to people that the electric field vector depends on where you're located. It depends on your position. All right, electrostatic field. Remember, gravitational field was gravitational force per unit mass. Electrostatic field is electrostatic force per unit charge at a point in space. And if gravitational field was gravitational force per unit mass with unit of Newton per kilogram, then electrostatic field as electrostatic force per unit charge has to have an SI unit of Newton per coulomb. Newton per coulomb. Unit of force divided by the unit of charge. That's the SI unit of electric field, Newton per coulomb. Now, just like I talked about in the gravitational case, suppose you already know the electrostatic field E arrow at a location in space. And then someone comes along with their favorite pet particle and they tell you how much charge Q that pet particle has. And they put it at this location. Then I can use the electrostatic field that I already know to calculate the electrostatic force on that pet particle, F electric. And I just used the fact that at the location in space, I already know what the electrostatic field is, E, and the meaning of E, electrostatic field, as electrostatic force per unit charge. So I take E and I multiply it by the charge Q of that pet particle that the person put there. E in newtons per coulomb times Q in coulombs gives you newtons force. Okay? So if you already know E at a certain location, and somebody comes along with a particle of charge Q and puts it at that location, do Q times E to get the force on the particle. See how I'm arguing just like I did in the gravitational case? Gravitational case is using mass and gravitational field, and this case is using charge and electrostatic field. Now there is one complication in the electrostatic case that you don't have in the gravitational case. And that is that the property known as charge comes in two varieties, whereas mass comes in one. Who knows why? But charge comes in two varieties that we call positive and negative. And we do have to remember that. Your favorite pet particle might have positive charge. But your cousin's favorite pet particle might have negative charge. And so you do have to be careful that the sign of Q is important here. Let's talk about why. Let's say we already know at a certain point in space the electric field. Here we are at a certain point in space. And let's say the electric field vector there, caused by some charges, sorry, that's a little bit out of view, isn't it? Is in the direction I've just drawn. And then you come along with your favorite pet particle and you put it at the X. Q is your pet particle's charge. What's the direction of the electric force on your pet particle? Answer is, it depends on the sign of the charge of your pet particle. If your pet particle has positive charge, then Q times E is a positive number times E, and it gives me a vector F in the same direction as E. Like that. But then your cousin comes along with her favorite pet particle, and it's negatively charged. The Q value for her particle is negative. Then when I do Q times E, the Q is a negative number. When you multiply a vector by a negative scalar, you get a new vector with the reverse direction. That's very important. So if the particle you put there, Q, has negative charge, then the electric force on the particle is opposite to the electric field. And we have to be alert to that possibility here with charge. Okay? All right, now, I've been trying to motivate why you want to know electrostatic field, because if you know it at a certain place, then when somebody comes along with a particle and puts it there, I can find the electrostatic force on that particle. But that does beg a question. How do I determine the electrostatic field E at a point in space to begin with? I got to know what it is before I can then go do Q times E to get F. How do I find E? And what creates E, electrostatic field? Answer, charge. Any charge. So I'm going to go through some steps. I'm going to use a Wiley Plus simulation to talk us through the definition of electrostatic field, how we think about it. And then the rest of this video will be about practicing with that, and then we'll be practicing in class. So let me go to the Wiley Plus picture, in which we're looking in the XY plane, and there's a lot of stuff in here, but a lot of symbols, but there's only one actual object we're talking about. We'll call it a particle that's sitting at the origin of an X in the XY plane. X to the right, Y upward, Z coming straight out towards us. And that particle at the origin has been fixed there, nail it down so it can't move. And it's got some amount of charge Q, and let's just, for the sake of being specific, say Q is positive. So that particle has positive charge and it's sitting at the origin. Just because of its charge, it creates in all of space around it, this particle does, an electrostatic field, which is a vector quantity with a magnitude and a direction. I have picked a basically arbitrary point that I have marked with an X and labeled P. See it there in red? I happen to choose it in the first quadrant. I do have to tell you where that point P is. I also have to tell you where the source particle is, but I did that. It's at the origin. The point P, which you could call the field point, the point where we're going to find the electrostatic field, has coordinates x, y, where both happen to be positive. There's a position vector, r arrow. I also labeled it r sub p, just to try to emphasize it's the position vector for point P, would be x times I hat plus y times j hat. And you can even talk about a unit vector, rp hat. which has magnitude 1 and points in the direction of r. And I drew it anchored at point P, but you could draw it anywhere. The main thing is it points in the direction of the r. Okay, we're going to work our way conceptually through figuring out the electrostatic field at that point P. And if we can do it then at point P, we ought to be able to do it at any other point too. All right, here's the next step. Okay, we have come along with what we're going to call a test particle. And we're going to anchor it at point P. Before, there was nothing actually located at point P. Now I've put another particle there called a test particle. Anchored it there. And by definition, it has positive charge in an amount Q0. That's just the convention for labeling its charge, but it's positive. Okay? And we ask the following question. What is the electrostatic force on the test particle due to the source particle? Now, we learned how to calculate that in chapter 21. Coulomb's law enables us to calculate the electrostatic force on one particle due to another. And I show that arrow for the electrostatic force on the test particle. It's that big blue arrow labeled F electric. Notice it's anchored on the test particle, and notice it points radially away from the source particle because they're both positive, and the force is repulsive. And then I just wrote down the formula using Coulomb's law for that electric force. Q0 times Q times R hat over 4 pi epsilon 0 R squared. Coulomb's law, chapter 21, previous video lecture. We know how to calculate that F electric using Coulomb's law. Okay? So now we know what that is conceptually. So let's go to the next step. Now, define the electrostatic field at point P due to the source particle. Remember, it's that source particle at the origin that's creating the electric field everywhere. Here it is. E arrow is defined to be, now remember what I said it was, electrostatic force per unit charge, and per means divide. So take the F electric on the test particle, formula I just wrote down, and divide it by the amount of charge of the test particle, Q naught. So F electric over Q naught. And then, if you go back to the formula for F electric, there it is, and divide that by Q naught, it just cancels out that Q naught in the numerator, and the resultant formula is for the electric field, E, at the point P, due to only the source charge. And it is given by the charge Q of the source charge times R hat over 4 pi epsilon 0 R squared. And since the F electric that we just found pointed radially away from the origin in this case, and the E is F electric over Q naught, and Q naught is positive, then the E points radially away from the origin at point P. And there it is in red. Anchored at point P, that arrow is representing the electrostatic field at point P, and it points radially away from the source charge. Okay? So you are to think of that vector EEP as a property of the space at point P, and that it is caused by the source particle with charge Q. So the formula for E depends on Q, but not on the test charge amount, Q0. The test charge was just used to detect the electric field. And the detector can't influence the thing being measured. And it was E that was being measured. All right, so that formula in the box, which we're going to come back to on our slides, is the formula for this chapter. It is telling us how, we'll have to practice with it, but it's telling us how to calculate the electrostatic field at any point due to a source particle. Now, here's the payoff I was talking about. Now that you know the electric field at the point P, there it is in this new picture, pointing radially away from the source, What if somebody comes along with their favorite pet particle and puts it at point P? I've drawn it there now as a big red disk. That's supposed to represent the pet particle that somebody put there. The source particle was already there, remember? Somebody came along, maybe when I wasn't looking, and put their favorite pet particle at point P. That's the red disk. Well, that red disk, that point particle, which we're going to call the detector particle, is immersed in the electric field of the source particle. And at the place where it is, that electric field is EP. We can now calculate the electrostatic force on the PET particle, the detector particle, using F electric, using the concept of electrostatic field as force per unit charge. So take the electrostatic field at point P and multiply it by the amount of your PET particle's charge. I called it Q prime because I don't want to confuse it with the source charge Q. And F electric is Q prime times EP. And I, just to be tricky, assumed that the PET particle, the detector particle, the red disk, had negative charge. So that Q prime was a negative quantity. So then Q prime times EP is a force, a vector, F electric, that is opposite to EP. And that's the blue arrow there. And that's the direction of the electrostatic force on the detector particle. This is the kind of thing we're going to do all the rest of this chapter, this kind of thinking. Okay? Now, I just picked a point P in the first quadrant to think about the electrostatic field and the electrostatic force that might then act on a detector particle. But of course, you could do this same game at any point in space. And there's an electric field E arrow at every point. And so you really need to map out, as it were, the electric field or electrostatic field at a whole bunch of points to try to visualize it. The electrostatic field created by that source particle at the origin. So I've done that here. Okay? Now, the way I did it here, using a program called Mathematica, is I represented the electrostatic field as a bunch of arrows at any given location. The bigger the arrow, the bigger the magnitude of the electrostatic field. And then the arrow's direction is the direction of the electrostatic field. Notice the arrows are bigger as you get closer to the source charge and smaller as you get farther away. That's because the electrostatic field, there it is in the red, created by a source charge Q, gets weaker as you get farther away. How do I know that? Because of the r squared in the denominator. You double the distance from the source charge, and you'll reduce the electric field by 1/4. Okay? So as you get closer to the source charge, the electric field gets stronger. Okay, so now let me get back to my slides. Okay, and now we are to this important result. I've got it here in the red box, and it is the result for the electrostatic field created by a charged particle Q at a point labeled P. E arrow, and I add that subscript P. The books don't tend to do that, just to emphasize that you have to pick the point. You call it P or whatever you want to call it, but you got to tell us where the point is. The electric field depends upon the point where you're at. And the formula for calculating it is Q over 4 pi epsilon 0 r squared times r hat. So let me show you another picture of what I'm thinking about. I've got an XY coordinate system where, just so that it's not too complicated, I just picked the first quadrant to look at. The plus z-axis will be coming out of the screen towards you. And I took a source particle with charge Q at coordinates x comma y, and I put it somewhere. And just to be different, I didn't put it at the origin. Everybody said that source particle has to be sitting at an origin. Then I picked the point P to be just some distance away from the source. Now I need to tell you both where the source is, that'd be the coordinates x, y, and where point P is. with coordinates xp, yp. Then the position vector that the formula calls rp, arrow, points from the source particle to point P. And rp hat, the unit vector, just points in the direction of rp arrow and is drawn at point P. And then you use that formula to get the E there. You take Q over 4 pi epsilon 0 times r hat. You have to figure out how to get basically the magnitude and direction of that E. And, or its x and y components. You've got to be able to deal with the fact that E is a vector. Here's one thing we can say right away. The direction of the electric field at point P is determined by the sign of Q. If Q is positive, right, meaning this number right here is positive, then the direction of the electric field is the same as r hat, which means radially away from the source. So if I go back over here, now let me get rid of some things so that it's not too cluttered. And let's say the source particle is positive. Then the electrostatic field at point P is radially away from the source particle. Same direction as the r hat. But what if the source particle Q is a negative value? Then the Q in that formula is a negative number, and E is exactly opposite to r hat at point P. So the E arrow would be that way, towards the source. Okay? That's a very important point. Radially toward Q if Q is negative, and radially away if Q is positive. So if I had a point particle sitting somewhere, like right there, and I told you it's positive charge, then you ought to be able to sketch the direction of electrostatic field vectors at various locations, like this point P here, or another point here, or a point up here, or a point over here. You ought to be able to sketch the direction of the E if I tell you Q is positive, and maybe and sketch the direction of E if I tell you Q is negative. Okay? Because there's an arrow at every point in space, like I showed you in that Wiley Plus animation. And of course, that pretty quickly gets hard to visualize. You have to visualize a whole bunch of arrows. So we do have, last thing I want to tell you in this lecture, we do have a way to help us visualize the electrostatic field of a certain charge configuration. And it's called electric field lines. Now these are completely human constructed, just to help us visualize the actual physical thing called the electrostatic field. So electric field lines as a way to visualize electrostatic field. Lines. Human construct to help us visualize electrostatic field. So the drawing shows a kind of a spherical object, and there's a bunch of negative signs written around it. What they're trying to tell you is this object has some net negative charge. Oops, sorry, let me bring that down just a little bit. It has some net negative charge that is spread out around it pretty much uniformly, it looks like. And so that would create an electrostatic field all around, and we'd like to visualize it. Okay? One way to do that is to draw what are called electric field lines for the charge distribution. Remember, negative charge, the electric field points radially toward the charge. You know that because if you put a positive test charge at a certain location, like right there, positive test charge, the direction of the force on it would be towards the charge. By definition, that's the direction of the electrostatic field at that location. All right, so then the picture right below is that same spherical object with the same charge and a bunch of electric field lines that have been drawn to help us visualize the electrostatic field. Okay, now, I've got 4 properties that we need to know about electrostatic field lines. First, about direction. You see all these lines drawn down to here in blue? They all have arrows on them, don't they? These lines happen to be radially straight. They won't be that way in every charge configuration, but they are here. Okay, to get the actual electric field vector at a particular point, it's a vector that is tangent to the electric field line at that point and in the direction given by the arrow on the electric field line. So if I pick a point in space, like right there, then the actual electric field vector there is tangent to the field line through that point and pointing inward because the electric field line points inward. So you could come over here and say sketch the electric field on that electric field line, and it would be tangent pointing inward. Or you could come over here and ask to sketch the electric field, wherever. It's tangent to the electric field line through that point. Here's another thing to know. The greater the magnitude of the charge, the more electric field lines are drawn. It's kind of like a scale on a map. I didn't make this electric field line drawing, but I did count, and there are 32 electric field lines that are drawn pointing inward. Somebody just chose that, like a scale on a map is chosen arbitrarily, right? I draw a map of the United States, I have to decide the scale, right? 100 kilometers on real ground has to correspond to some distance on the map, and I have to pick that. And it's purely arbitrary. Same thing here. Somebody has to kind of pick a scale. Right? Now this sphere was drawn with a certain amount of negative charge on it by those minus signs distributed. And then they drew 32 field lines. So the way you would deal with the scale here to be consistent is, if you had a sphere with half the amount of charge as this, you would only draw 16 field lines, half the number. Okay, once you have a scale, one thing to note is the closer the field lines are together, generally speaking, the stronger the field. So you see as the lines get closer to the sphere, they get more bunched up. That's telling you the field is getting stronger. Here's another property of field lines. They can never cross. You can't have a situation like that where those blue lines with arrows represent electric field lines, and there's a place right there where they cross each other. You can't have that because that means the direction of the electric field's ambiguous at the crossing point. Is it in the direction of that field line, or is it tangent to that field line? Which way is it? There's got to be one direction for the electric field at a point in space. So electric field lines can never cross. And generally speaking, electric field lines begin on positive charge and terminate on negative charge. Look at our drawing over here. All those electric field lines terminate on the sphere, and the sphere has negative charge. And no, electrostatic field lines do never just begin out of empty space like this drawing shows. That's just artistic license. Somewhere out there, there must be positive charge for the field lines to begin on. They just aren't. It just isn't drawn. Now this spherical object is kind of point-like, and the electric field points radially in. Let's take something a little more complicated and not point-like. A positively charged, large, non-conducting, that means insulating, sheet. So that might be a very wide, very long, very thin sheet of plastic wrap, cling wrap, the kind that you peel off and then rip. But imagine it's very big and flat. It's easy to get charge built up on that cling wrap. That's how it works. What would be the electric field created then by, and cling wrap is electrical insulating material, not conductive. So what would the electric field look like for this big flat sheet of charge? Let's say it's positive charge. Here's a drawing of it, but it's kind of a perspective view. Here's the sheet. Okay? Flat, thin, extending on and on that way, and although they don't really show it, up that way and down that way. And the little plus signs evenly spaced are saying it's got evenly distributed positive charge. What do the electric field lines look like for that? Okay, we're just going to tell you now. We'll explain later on how we know this is the result. But look at the picture in part B. Still the perspective view of the sheet. And I just see lines pointing to the right and to the left of the sheet, away from it, on either side, and just pointing straight away, perpendicular to the surface of the sheet. On the right side, they point to the right, away from the sheet. On the left side, they point to the left, away from the sheet. You can pick a point, like right there, and you can deduce that the electric field vector at that point is tangent to the electric field line through there in the direction of the arrow on the field line. Here's a side view of that sheet. Now it goes on, this way, and towards us and into the page, into the sheet, but thin this way. See the little plus signs going along it? They happen to be on one edge there, but that's okay. Evenly distributed all up and down. And the electric field vectors point on the right side to the right and on the left side to the left, perpendicular to the sheet and evenly spaced. That's also important. So that's a large, non-conducting, i.e. insulating sheet with positive charge. One more set of pictures. A set with 2 point particles, 2. The first picture is 2 positively charged point particles with equal charge. We're just showing you the electric field line so you can see. Rather interesting looking, right? The region in here in the middle, not where the E is, in the middle, like that, like in here, where there aren't any field lines, they're telling you the electric field in there is very weak. In fact, if you're exactly at the midpoint, if you imagine a line connecting them, and you're exactly at the midpoint right there, the electric field's exactly 0. The electric field is strong when you're at points near each charge, except right in the middle area there. And then it gets weaker as you go away from the charges. You could pick a point like right there, and the electric field vector at that point is an arrow that's tangent to the field line at that point. Now the field line curves, but the electric field arrows don't curve, you just draw an arrow, but it's tangent to the field line. And the last picture is really important. It's also 2 point particles, but one's positive and one's negative. And equal amounts, plus Q, and the other one would be minus Q. Equal but opposite amounts of charge. That configuration specifically is called an electric dipole. We're going to study that quite a bit. But we want you to see the electric field line picture for it, so you can try to visualize the electric field. Note now, the electric field is quite strong in the region between the 2 point particles, and then gets weaker as you go farther out. You could pick a point, like right there, and you know the electric field vector would be tangent to the field line through that point, which would be that way. Okay, so those are some electric field lines. We'll be working with pictures like this, and we'll be studying some of these charge configurations in this and the next chapter. Okay, but that's all for this video.